Hello everyone, my name is Sanjana Vinayaka. I am a doctoral student in the Department of Civil and Environmental Engineering in the University of Massachusetts, Lowell. I will be presenting my poster Comparison between Contact and Remote Crack Detection using GPR and SAR. The results put herein are the part of the TIDC Project 1.4 Electromagnetic Detection and Identification of Concrete Cracking in Highway Bridges. This work wouldn't have been possible without my fellow researcher Ahmed Al-Zayadi and my advisor Dr. Zhuang Yu. Cracking of concrete is inevitable and is commonly seen durability issue of concrete bridges in the US and around the world. The size and the location of cracks on a concrete bridge indicate their structural significance and are vital to the structural health of concrete bridge. One of the most critical challenges for the durability and life expansion of concrete highway bridges is crack detection and quantification. Well, the crack length and crack width can be statistically measured on the surface of concrete bridges through visual inspection. Crack depth usually remains unknown without the use of destructive testing. With the use of non-destructive evaluation techniques such as microwave and radar sensors, subsurface sensing can be achieved in concrete structures. In this study, we will be using two different types of radar sensors. The first, ground penetrating radar, which uses the contact technique. Second, the synthetic aperture radar or the SAR, where inspection can be carried out remotely. And also, the quantitative comparison between the contact ground penetrating radar images and the remote synthetic aperture radar images for the concrete crack detection is presented in this poster. While the concrete cracks are highly random and the geometry varies considerably, we begin our preliminary study by studying the artificial cracks of regular geometry in the laboratory conditions. 4 concrete panels, panel CNI, CNC, CNCD and CNCW of dimensions 30 by 30 by 4 cm were cast and artificially cracked were introduced at exactly center of these concrete panels. The dimensions of the 3 artificial cracks as well as the concrete panels are as shown in figure 1. Panel CNI is intact and there is no crack on this panel. Panel CNC has a crack length of 10 cm, width of 0.5 cm and depth of 0.5 cm. In panel CNCD, the length and the width are kept constant as in CNC, only the depth is increased to 1.5 cm. In panel CNCW, the length and depth are kept constant as in CNC, only the width is increased to 2 cm. All the 4 specimens were scanned using 10.5 GHz SAR imaging sensor remotely inside an anechoic chamber. The distance between the SAR antennae and the concrete specimen was 30 cm. Also, the same concrete panels were scanned using 1.6 GHz GPR by placing the panels side by side on a concrete floor. This provided a better runway for the GPR inspection. Both the SAR image and the GPR image is shown in the range and cross-range domain is shown in figure 2 and figure 3 respectively. It can be observed from these images that the reduction in SAR amplitude as well as GPR amplitude is found in the artificially cracked specimens. Several image processing techniques were carried out for figure 3 And a background subtraction was applied to the figure 3 by considering signal from the intact specimen as a background and removing it throughout the image yielded the figure as shown in figure 4. Also, the SAR contours at 3 different SAR amplitudes of 700, 800 and 900 were extracted from figure 2 and is as shown in figure 5. When GPR detects a surface crack in concrete, a hyperbolic pattern of reduced GPR amplitudes can be found as shown in figure 4. When SAR detects the same surface crack in concrete from a distance, the background surface reflection is usually too strong to be used for the damage detection. Rather, the background backscattering signals are amplified and are superimposed in the sub-images in SAR. This is manifested in change in the SAR contours at 3 different SAR amplitudes shown in figure 5. Figure 6 compares the contact GPR inspection scheme with the remote SAR inspection scheme. Figure 7 shows the hyperbolic scattering in the GPR images and the backscattering pattern in the SAR images. It can also be seen from the figure 5 that the contour for the intact specimen is almost regular, but the contours at the same amplitude level for the cracked specimen are usually undulated and there is a significant variation in their shape. By this, we can conclude that the presence of surface crack will generate a hyperbolic scattering in the GPR images, but for the SAR images, a semi-sinusoidal pattern is observed. To better describe this continuous hyperbolic pattern in the GPR images, local minimum points were extracted and modeled with a second-order polynomial function. Table 1 summarizes the result for all the 3 cracked specimens CNC, CNCD and CNCW. The second-order polynomial equation is shown and also the curvature of this equation is found out, and also the inverse of the curvature represented by 1 by k is found out. We can observe that the characteristic width of these second order polynomial equation increases with the increase in the volume of the crack. This characteristic width is less for the specimen CNC with a volume of 2.5 cm cube and has more characteristic width of these hyperbola for specimen CNCW with the volume 10 cm cube. We could then compare this inverse of a curvature of the cracked signal to the volume of crack and extracted the equation for the depth of crack as shown in figure 1. The depth of the concrete crack can be found out by using equation 1. From this study, we can conclude that both the contact GPR and the remote SAR can be used to detect the presence of a surface crack and also to quantify the depth of the concrete panels. Presence of a surface crack will generate a hyperbolic scattering in GPR images, but for the SAR images, a sinusoidal pattern is observed. Thank you.